Let's take a look at section 5.2, logarithmic functions. Now in the last section we talked about the exponential function and the fact that the basic form for the exponential function equation would be f of x equals b to the x power, where b was a number greater than 0 and b could not equal to 1. Well, if you recall the exponential function, this was the basic graph if b was a number greater than 1. This passes the vertical line test, so we know it's a function, but notice it also passes the horizontal line test. Therefore, we know it's a one-to-one function, which means it has an inverse. Well, how do you go about finding the inverse of a function? If you remember from the previous chapter, if I give you the equation and ask you for the inverse equation, all you do is switch the x and the y. So notice if you switch the x and the y, you would end up with this. X equals b to the y power. What we then did in the previous chapter was we would then solve for y. But if you notice here in this example, trying to solve for y, we're unable to. There aren't any algebraic operations that we can perform that we normally do for solving equations, like adding or subtracting, multiplying or dividing the same thing from both sides. None of those things would help us solve for y. So, since there's no way for us to algebraically do that, we have a notation that we're going to use to express what y is representing. And if you notice, y here is the exponent that we have to raise base b in order to get x. I have that written for you here. Y is representing the exponent that we raise base b to get x. So we're going to use logarithmic notation to express what y represents. Y is, when you see the word logarithm, I want you to think exponent. Y is the exponent that I have to raise base b in order to get x. X is referred to as the argument or the result. So this statement here can be rewritten in logarithmic form like this. One of the first things that they're going to have you do is get used to going between logarithmic notation and exponential form. Now this is the basic logarithmic function and we're going to learn more about it in this section. Notice the restrictions are the same as they were for the exponential, that b has to be greater than 0 and b cannot equal 1. Now also recognize that the domain for the logarithmic function has to be greater than 0. This is going to be important for you to remember. Taking a look at the first types of examples that you will encounter, going from exponential to logarithmic form. So this is an exponential form and they want us to rewrite it in logarithmic form. Just realize you have three components that you're going to rewrite in this format. So the exponent y is going to come here, then followed by the equal sign, logarithm. The base b is written as a subscript, so the base b is going to be transferred here, and the argument x, or the result, is going to be next to it. So taking a look at this example, notice what we have here. The exponent of -3 is written here. Then we have the equal sign. The base 2 is written here as a subscript. And then finally, the argument or the result is written next to it. So this is the same thing in exponential form and in logarithmic form. Taking this and doing the same thing, the exponent comes here, followed by the equal sign. The base is written here as a subscript, and then the result, the argument, is written next to it. Notice in these examples, they give us the problem in logarithmic form and we have to transfer it back into exponential form. I like to start with the base, so he's the easiest to identify. The base 7 raised to the power 3 is going to equal the result 343. The base a raised to the power of 3 is going to equal the result of x minus 1. Now taking a look at some general properties involving logarithms. Remember to think exponent and think about the exponent rules that you're already familiar with. So here this is saying log base b of b equals 1. Well, if I write this in exponential form, we're just simply saying base b raised to the power of 1 equals the result of b. And isn't that true? In this one, base b raised to the power of 0 is equal to the result of 1. Isn't this true? Remember the rules for raising things to the 0 power. All right, take a look at these examples here and keep in mind that when you see logarithm, you're thinking exponent. So this is the question that you would ask yourself for a problem like this. What is the exponent that I'm raising base 2 in order to get the result of 8? What would that exponent need to be? And in this case, 3. What is the exponent that I have to raise 6 to get the square root of 6? What is the exponent that I have to raise 3 to get 1 over 9? Now in these examples you may or may not know the answer right away like you did here, so if you want to write it out as an equation, we're looking for the exponent. So we're looking for the y equals log base 6 of square root of 6. Rewriting this in exponential form, we'd have 6 to the power y equals the result square root of 6. So all I did was transfer this from logarithmic form to exponential form. Now, if you remember in the previous chapter, you learned to relate the bases. So if I could get both sides written in terms of the same base, I could drop the bases and set the exponents equal. So notice this square root of x could be rewritten as, this square root of 6 could be rewritten as 6 to the 1/2 power. Now that the bases are the same, I can drop them and say y must equal 1/2. In other words, the exponents must equal. Here, rewriting the problem as an equation to solve for y, rewriting this in exponential form, we'd have 3 to the power y equals the result 1 over 9. The 9 could be written as 3 squared. The 1 over 3 squared could be rewritten as 3 to the negative 2 power using basic exponent rules. Now dropping the bases because they are the same, we have y is equal to negative 2. Now take a look at what we call the cancellation properties. This here is saying b to this power equals x. Well, what is this actually representing? Notice it is representing an exponent that I'd have to raise b in order to get x. So if that's the case, when you raise b to this, you're going to get the result x. Here's an example. This is representing a number, an exponent that I have to raise 2 in order to get 11. Well, if you raise 2 to this, you would get 11. Let me show you another example that you could actually calculate in your mind. Let's say we had 2 log 2 of 8. This is representing an exponent that you'd have to raise base 2 to get 8. Do you know what that exponent is? It would be a 3. So all of this is representing the number 3. So if you raise 2 to the 3rd power, what do you get? 8. We want to be able to go from here to here using this property, realizing that when we see this, this is representing whatever's necessary to raise 2 in order to get 8. So if you raise 2 to this, you're going to get 8. Just like in this example, how we got 11. All right, this property is saying, if I write it in exponential form, b, the base, to the power x is equal to the result b to the x. Pretty straightforward. Well, let's take a look at these examples over here. Again, asking the question, what is the exponent that you have to raise that particular base in order to get the result they want? So what exponent do I have to raise base 4 to get 4? The answer is 1. What do I have to raise 9 in order to get 1? What exponent would I raise the 9 to get 1? 0 is correct. All right, so what we have here is the common logarithm. These happen so very often in real-world problems that they've been assigned special symbols and names. The common logarithm is when the base is 10. And so we don't bother writing the base. When it's not there, you are to assume that it is base 10, the common log. You'll notice this is the one you see on your calculators. The other one that occurs in a lot of real-world problems is the natural logarithm, and the base there is e. And so for natural log, think L and N, natural log, we're going to represent it with L and N. We don't bother writing the base e. As soon as you see ln, you know that it refers to the natural log and the base is e. One piece of advice, remember that this is an L and an N, like the name L for logarithm and N for natural logarithm. So be careful when you're typing in on the computer that you don't type in an I instead of the L. Make sure you are typing a lowercase l and a lowercase n and not a capital I and N, all right? All right, so one of the things that you're going to be asked to do in this section is to write each exponential as a common log or a natural log, very much like what we were doing in the beginning. It's just now we know how to write the common and natural log. So here, taking this exponential and put it in logarithmic form, we'd have base 10, so we're going to use log. Notice we did not write the 10 here, it's assumed to be there. So log base 10 of the argument 1000 should equal the exponent 3. Here we have the base is e, so we use natural log of the argument, which is 1 over e, equals the exponent of 1. All right, so there's the argument, there's the exponent, the base we don't even have to fill in. It's assumed as soon as we write ln. So once again, ln is the base, so we just write ln of the argument 2 is supposed to equal the exponent k. All right, here these are written in logarithmic form, and to translate them into exponential form, we have to recognize what base are we talking about. Well, since this is ln, we know this is base e. So e raised to the 0 power equals the argument of 1. Here we have log. Notice there's no number there, so we know that that is base 10. So 10 to the 6th power equals the argument of 1 million. All right, taking a look at these examples, they want us to evaluate them without using a calculator. And so just like the other ones we did, we're being asked the question, what is the exponent that you'd have to raise the base in order to get that result? Well, what is the base here? Since it's log, the base is 10. So what would I have to raise 10 to? Notice I put the question mark here for you to ask yourself, what does that exponent need to be so that I can get the result of 10,000? It would be 4. 10 to the 4th power equals 10,000. Once again here, what is the exponent that I'd have to raise 10 in order to get 1 over 1,000? Well, if we rewrite the bases the same, 1,000 can be written as 10 to the 3rd. This can then be written as 10 to the negative 3. So therefore, the unknown exponent that we were looking for, which we could have written a y here if you wanted, y is equal to negative 3. Another example, the base here must be e because we're dealing with ln. So what do I have to raise e to in order to get 1 as a result? And so the exponent here would be 0. E to the 0 power equals 1. You're going to be asked to sketch the logarithmic function. So here's the basic form of the equation. You can add this to our list of different types of equations that we learned back in chapter 3. Now we know the exponential and we're about to see the logarithmic function. So taking a look at the basic graphs that we have here, this will be your logarithmic function when the base is greater than 1. So I like to say an increasing logarithmic function. This will be your logarithmic function when the base is a number between 0 and 1, or I like to say a decreasing logarithm. Now these logarithms have a vertical asymptote, which is a value that the function approaches but never actually reaches, and that is at x equals 0. If you recall,